Imagine a cat trapped in a box with a radioactive atom that has a 50% chance of decaying within a certain time frame. If the atom decays, a poison is released, killing the cat. But what if we don't open the box? Is the cat alive or dead? This thought-provoking concept, known as Schrödinger's cat, has been a cornerstone of quantum mechanics since its inception in 1935. The idea was first proposed by Austrian physicist Erwin Schrödinger, who sought to illustrate the seemingly absurd consequences of applying quantum mechanics to everyday objects. Schrödinger's cat is a thought experiment designed to highlight the paradoxical nature of quantum superposition. In the experiment, a cat, a flask of poison, and a radioactive source are placed in a sealed box. The radioactive source has a 50% chance of decaying within a certain time frame, which would trigger the release of the poison and kill the cat. However, according to quantum mechanics, the radioactive source is in a state of superposition, meaning it is both decayed and not decayed at the same time. This, in turn, means that the cat is also in a state of superposition, being both alive and dead simultaneously. The concept of Schrödinger's cat raises fundamental questions about the nature of reality and the role of observation in quantum mechanics. If the cat is in a state of superposition, then what happens when we open the box and observe it? Does the act of observation itself cause the superposition to collapse, resulting in the cat being either alive or dead? This paradox has sparked intense debate among physicists and philosophers, with some arguing that the cat's fate is sealed from the moment the box is closed, while others believe that the act of observation is what ultimately determines the outcome. Erwin Schrödinger, an Austrian physicist, first proposed the thought experiment in 1935. At the time, Schrödinger was engaged in a heated debate with Niels Bohr and Werner Heisenberg, two prominent physicists who were developing the principles of quantum mechanics. Schrödinger's cat was intended as a critique of the Copenhagen interpretation of quantum mechanics, which suggested that a quantum system remains in a state of superposition until observed. Schrödinger's goal was to illustrate the seemingly absurd consequences of applying this principle to everyday objects, such as a cat. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that a quantum system remains in a state of superposition until observed. This means that, in the case of Schrödinger's cat, the cat remains both alive and dead until the box is opened and the cat is observed. The Copenhagen interpretation is one of the earliest and most widely accepted interpretations of quantum mechanics, but it has been subject to criticism and controversy over the years. Some physicists argue that the interpretation is incomplete or inconsistent, while others believe that it provides a fundamental insight into the nature of reality. The measurement problem is a fundamental challenge in quantum mechanics, which questions what happens when a quantum system is measured or observed. In the case of Schrödinger's cat, the measurement problem arises when we open the box and observe the cat. Does the act of observation itself cause the superposition to collapse, resulting in the cat being either alive or dead? The measurement problem has sparked intense debate among physicists, with some arguing that the act of measurement is what ultimately determines the outcome, while others believe that the outcome is predetermined from the moment the box is closed. While Schrödinger's cat is a thought-provoking concept, it raises questions about the applicability of quantum mechanics to everyday objects. Can we really expect to see quantum superposition in objects like cats or even larger systems? The answer is no, at least not in the classical sense. Quantum superposition is typically observed in very small systems, such as atoms or subatomic particles. However, researchers have been able to demonstrate quantum superposition in larger systems, such as superconducting circuits or optical systems. Researchers have conducted numerous experiments to demonstrate quantum superposition in various systems. One notable example is the quantum eraser experiment, which involves entangling two particles and then measuring the state of one particle to determine the state of the other. These experiments have consistently shown that quantum superposition is a real phenomenon that can be observed and measured. However, they also raise questions about the nature of reality and the role of observation in quantum mechanics. One of the most fascinating interpretations of quantum mechanics is the many-worlds interpretation, which suggests that every time a quantum event occurs, the universe splits into multiple parallel universes, each with a different outcome. In the case of Schrödinger's cat, this would mean that the cat is both alive and dead in separate universes. The many-worlds interpretation is a mind-bending concept that challenges our understanding of reality and the nature of the universe. The role of observation in quantum mechanics is a topic of ongoing debate among physicists. Some argue that observation is what ultimately determines the outcome of a quantum event, while others believe that the outcome is predetermined from the moment the system is created. The concept of Schrödinger's cat highlights the importance of observation in quantum mechanics, as it raises questions about what happens when we observe a quantum system. Does the act of observation itself cause the superposition to collapse, or is the outcome predetermined? The concept of Schrödinger's cat has far-reaching implications for our understanding of reality and the nature of the universe. It challenges our classical notions of space and time and raises questions about the role of observation in quantum mechanics. The concept also has practical applications in fields such as quantum computing and cryptography, where the principles of quantum mechanics are used to create secure communication systems. As researchers continue to explore the mysteries of quantum mechanics, the concept of Schrödinger's cat remains a thought-provoking and fascinating topic of study. The debate surrounding Schrödinger's cat continues to this day, with physicists and philosophers arguing about the implications of the thought experiment. Some argue that the concept is a fundamental challenge to our understanding of reality, while others believe that it is a mere thought experiment with no practical applications. As researchers continue to explore the mysteries of quantum mechanics, the concept of Schrödinger's cat remains a topic of ongoing debate and discussion. The question of what happens when we observe a quantum system remains one of the most fascinating and complex questions in all of physics. Picture a simple wooden box with a lid that closes completely. Inside sit three things: a living cat, a small flask filled with poison, and a tiny fragment of radioactive material. A monitoring device rests beside them, ready to react to the faintest signal from that material. The box is sealed so that nothing from the outside can interfere, and no observer can see within. What happens next depends entirely on events too small for the eye to witness. At the heart of the experiment lies a single radioactive atom. In the strange mathematics of quantum mechanics, such an atom has no fixed state of decay until it is measured. It exists in a superposition, a blend of having decayed and not having decayed at the same time. Over the course of an hour, the atom may or may not release a particle. That single undecided event is what links the fate of the cat to the laws of the subatomic world. A Geiger counter sits inside the box, wired to detect radiation. If the atom decays, the counter clicks and triggers a mechanism. If the atom does not decay, the counter stays silent. The device is the bridge between the quantum scale and the everyday world. It is the point where a subatomic possibility becomes a mechanical action, and where the chain of cause and effect begins. Connected to the counter is a small hammer and a fragile flask of poison. Should the counter register a decay, the hammer swings and shatters the glass. The released poison would then fill the box and end the cat's life. If no decay occurs, the flask remains intact and the air stays clear. The cat's survival is therefore not a separate event, but a direct consequence of a quantum chance. Before the box is opened, the mathematics of quantum theory describes the cat as both alive and dead simultaneously. This is not a trick of language, but the literal meaning of superposition applied to the contents of the box. The wave function that represents the system contains both outcomes at once. To the theory, the cat is not one thing or the other, but a combination of both possibilities held in suspension. Erwin Schrödinger proposed this scenario in 1935 during correspondence with Albert Einstein. The two men were uneasy with the dominant interpretation of quantum mechanics advanced by Niels Bohr and Werner Heisenberg. Schrödinger designed the cat not to celebrate the theory, but to expose what he saw as its absurd consequences. He wanted to show that applying quantum rules to ordinary objects led to a conclusion that made no sense in daily life. The central puzzle is known as the measurement problem. When does the blurred superposition of alive and dead collapse into a single definite result? Opening the box forces one outcome, but the theory offers no precise moment for that change. Different interpretations of quantum mechanics answer this in different ways. Some place the collapse at the act of observation, others deny it ever truly happens. Schrödinger never intended for a real cat to be placed in such danger. The cat was a stand-in, a way to make the behavior of atoms imaginable to a general audience. In actual laboratories, experiments with particles and atoms have shown superposition to be real at tiny scales. A cat, being a vast assembly of atoms, would be extraordinarily difficult to place in a true quantum state, and no such experiment has been performed. The interpretation Schrödinger criticized is often called the Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg. It holds that quantum systems do not possess definite properties until they are measured. The cat appears alive or dead only when an observer checks. To Bohr and Heisenberg, the paradox was not a flaw but a reflection of the limits of describing quantum reality in ordinary terms. Over the decades, physicists proposed alternatives to explain the cat. Some suggest the universe splits, with one version alive and another dead. Others argue that interaction with the environment quietly resolves the superposition. Each interpretation uses the same mathematics but tells a different story about what is real. The cat remains a testing ground for these competing visions of nature. Beyond physics, Schrödinger's cat escaped the laboratory and entered popular culture. It appears in books, films, and everyday conversation as a shorthand for uncertainty and hidden outcomes. The image of a cat that is both alive and dead captures the public imagination because it places the strangest part of modern science into a familiar scene. The thought experiment became a symbol of how little we intuitively grasp the quantum world. Nearly a century after Schrödinger wrote his letter, the cat still sits in its box. The experiment was a critique, yet it became a foundation for ongoing debate about the nature of reality. We know superpositions exist for atoms, but we still ask how long they last and when they end. The sealed box remains open only in our minds, and the question it poses is still unanswered. If you enjoyed this story, subscribe for more real mysteries and discoveries.